Hey, welcome to The Explainer. You ever stop and wonder about the quiet magic that happens behind your screen? You know, how a crystal clear movie or your favorite song can just appear almost instantly from the cloud? It feels completely effortless. But it turns out there's a secret rule that governs our entire digital world.
No, really, think about it for a second. You hit play, and a file that should be absolutely massive, we're talking gigabytes, starts playing right away in beautiful high def. How on earth is that possible? How are we not waiting hours for it to download? Well, that's the big mystery we're going to unpack today.
Because what looks like an impossible stream of data, it's not magic. Not at all. It's actually a super clever, very calculated compromise that's happening billions of times a second, all over the planet.
And what's really incredible is that it doesn't matter if it's a video call, a song you're streaming, or even a satellite image. The exact same fundamental principle is running the show, balancing what you see with how fast you get to see it.
Okay, so let's get into it. This whole idea comes from a field called information theory, and it's something called rate distortion theory. It might sound kind of technical, but trust me, it's the hidden engine of our digital lives.
And this right here perfectly sums it up. Rate distortion theory is all about the unavoidable tug-of-war between two things. On one side, you've got rate, which is just how much you can shrink a file, and on the other, you've got distortion, which is the quality you inevitably lose when you do that shrinking.
So yeah, let's break down these two big players, rate and distortion. Because once you get the relationship between them, you basically unlock the secret to how almost all modern digital media actually works. And the trade-off is actually pretty straightforward when you see it like this. On one side, you've got the rate. That's the compression, how many bits of data you're using. The lower the rate, the smaller and faster the file. Easy enough, right? But on the other side is distortion. That's the quality loss, the measurable difference between the perfect original file and the squished version you actually get. So here's the key. To get that smaller file, you have to accept more distortion. But wait a second. Quality loss, that sounds a little subjective, doesn't it? Well, to an engineer, it's not a feeling at all. It is cold, hard math. They have super precise ways to measure exactly how much a file has been distorted. They use a whole bunch of mathematical tools to figure this out. You've got things with intimidating names like mean squared error, or MSE, Kullback-Leibler divergence, and something called a fidelity criterion. Look, we don't need to get into the nitty-gritty formulas, but the big takeaway here is that quality isn't just an opinion, it's a number you can actually calculate.
So, for example, using a measure like mean squared error, a high number like 87.4, well, that's a big red flag. It tells an engineer that there's a huge difference, a lot of error, between the original and the copy. And for you, that means you're going to see a pixelated image or hear some really muddy audio.
But a low number, something like 3.1, that's the goal. That means the file you're seeing or hearing is incredibly close to the original. High fidelity, low distortion. Honestly, the entire game of digital media is just trying to get this number as low as you can for the smallest possible file size.
So the big question is, how do they actually do it? How do engineers shrink these massive files while keeping that distortion number in check? Well, they've got a whole toolkit of really clever tricks to shrink data intelligently.
Here are three of the big ones. First up is quantization. Just imagine you have 100 different shades of blue and you group them into just 5 main blues. It simplifies the data. Then there's transform coding. This is a smart one. It focuses only on the things our eyes actually notice, like sharp edges, and kind of tosses out the tiny details we'd never miss anyway. And finally, there's sparse representation. This is like finding a super simple recipe to describe a really complex image, letting you get an almost identical result with way fewer ingredients.
And you know, this constant balancing act isn't just for your Netflix binge or your Spotify playlist. This trade-off between rate and distortion is absolutely critical in some of the most advanced fields out there. Take medicine, for instance. An MRI scan generates a mind-boggling amount of data. Rate distortion theory is what helps create algorithms that can compress that file so it can be stored and shared, but without losing the critical, life-saving details a doctor needs to make a diagnosis.
Or how about high-resolution radar? There's a technique called compressed sensing, which is built on these exact same principles that lets us build a super detailed image from way fewer signals than we used to need. That saves a ton of time and energy. It even gets into robotics. Engineers use this theory to calculate the absolute minimum amount of data a robot needs to get to stay stable and functional. If that information rate drops too low, the robot's control system gets distorted, and it could actually fail. It's a direct link between the data rate and the physical quality of its movement.
Which, brings us right back to the central theme of this whole thing, that constant, endless search for the perfect balance. This says it all, really. It is the fundamental law of digital information. You just can't have it both ways. If you want to make a file smaller and faster, you have to accept some loss in quality. And if you want perfect, flawless quality, you have to accept a gigantic file. Period.
So, the next time you stream a 4K movie without a single buffer, or you have a perfectly clear video chat with someone halfway across the globe, just remember, what you're seeing isn't an accident. It's a precisely engineered compromise, a single point that was carefully chosen on that rate distortion curve to give you the best possible experience.
And that kind of leaves us with the final thought. As our world generates more data than ever before, this trade-off is only going to get more and more important. So I'll ask you, what's your personal balance? In a world that demands everything instantly, what level of quality are you really willing to sacrifice for pure speed? That's the question that engineers, artists, and all of us will be answering for years to come.